Okay, how's it girls? I'm going to do some bond energy and bond length with you. So this is new notes. Please find them under materials, under classwork, or I have put it on the D6 communicator. Okay, so we're going to just start looking at bond energy and bond length first. You are going to need your shapes in this section, the molecular shapes, and your intermolecular forces. So that's why this has all been done. Okay, so bond energy, it's the amount of energy needed to break 1 mole of bonds. Now, I'm not talking forces here, I'm talking actual bonds, covalent, ionic, whatever, okay? So, the amount of energy needed to break a bond is equal to the amount of energy released when a bond is made. So, I want you to take note. Here I have 2 hydrogen atoms, molecules, okay? Their bonds have been broken. Here's an oxygen molecule that has been broken. So, this required energy. Okay, it needed energy to break. Then when it made its new bonds, so one of these oxygens then bonded with 2 hydrogens. When it made these bonds, it released energy. Okay, very important that you get that concept. To break a bond, you need energy. To make a bond, energy is released. Okay, so now that means that you can actually calculate the amount of energy. And you'll never have to learn this table like this off by heart, okay? I've put this on from the searched for a table. If you are asked to work out anything like this, you will be given some sort of a table, okay? You never have to learn it off by heart. So what we are doing is that we are going to see how much energy it's going to need to break and make bonds. What I do just want to say is if you are, let's say we want to break these bonds now between oxygen and hydrogen, and we know that it released a certain amount of energy, it will take the same amount of energy to now break those bonds than what it released. Okay, so over here we've got CH4. So if I had to draw it using Cooper notation, we know that methane looks like that. Okay, so I'm going to go, all right, so how much energy is going to be needed to break these bonds so that it can bond with something else? So if we take a look at this table on the side, there's a CH bond, 413. I have 4 CH bonds. So 4 times 413, and I get 4 times 413. I get 1,652 joules. Is it joules? If you look at the table, it says kilojoules per mole. So it's kilojoules per mole. Okay, so for us to break apart methane so that it can bond with another reactant, it will have to have 1,652 kilojoules of energy in order to break all those bonds. Okay. Here we have ammonia, all right, and if we take a look, oh damn, I don't have one on here, oh I do, okay, here's an HN, and it is 391 for an H and an N, and we've got 3 of them, so 3 times 391, okay, 3 times 391, 1173 kilojoules per mole. Okay, and so that's how much energy is needed to break up ammonia. Now we look at our water. Okay, water consists of 1 OH, 2 OHs. Okay, so 2 OHs at 463. And 463 times 2 equals 926 kilojoules per mole. Okay, so you will require that much energy to break the hydrogens away from the oxygens. Remember, we're talking bonds here, not intermolecular forces. Okay, so you can look at anything here and you can have different types of bonds. So if, for example, you have this, okay, this was the hydrogen cyanide. A triple bond between C and N will have a lot. I don't have that energy here, but you could work it out using that energy. It would be 1 of those and one of those. There you can see a nitrogen. Nitrogen would take 946 joules of energy to break them apart with their triple bond. Okay, so that brings us to bond length. So the distance between the nuclei of two covalently bonded atoms. So if I were to draw in the nucleus of each, and we take it from there to there, and we measure that distance, that would then be your bond length. Now, the stronger the bond, the shorter the bond length. I mean, that makes sense. And what happens is that we have, imagine my hands are like atoms, and so remember, we've got a lot of space because of those energy levels in that. So when our atoms or molecules bond, they collide with each other and they move into each other, but then their nuclei start repelling and they move out and then in, and then they can get stuck like that, and then that's their bond length. But obviously the stronger the force, the more they are in with each other, the weaker, the further away they are. Okay, so the stronger the bond, a stronger bond has a shorter bond length, and a weaker bond has a longer bond length. So if we have to look here, BR, that will have quite a big bond length. The distance between their two nuclei is higher because their bond is not so strong because of their energy being low. Whereas nitrogen, that would be quite close. So that would have a short bond length. The bigger the atom, the longer the bond length. That does make sense because they are just bigger. Okay. And therefore the lower bond energy. Double and triple bonds have higher bond energies and shorter bond lengths. Okay, page 2. Now, this is the crux of the matter here. This is where we're heading to. Okay, so we're talking about energy. Now we're going to go into more detail about the energy of reactions. Okay, so I want to clarify a few things first. So the first thing is the heat of the reaction. There's it's a term called the heat of the reaction. Sometimes it is referred to as enthalpy. Okay, sometimes it's considered as enthalpy, and it's a delta H. Now, I don't know if I've told you this before, but a delta, I think I have, yes, must have, in science means a change in. Okay, and when you have a change in, what is it? It's final minus initial. Okay, so the delta, which is that triangle, it's actually a Greek letter, is for the change in energy. Okay, and it is the net change, so the overall change of chemical potential energy of the system. So we talk about chemical potential energy of a reaction. And now we're going to look at exothermic versus endothermic. So I'm going to not look at the definition. I'm going to then go straight here. So if we have to take a look at overall endothermic reactions. So now remember, in order to break bonds, to make new bonds, energy is needed. Okay, so here you can see there's a lot of energy. Look at my little thin energies over here. So my reactants over here need a lot of energy. Okay, they have to absorb a lot of energy so that they can break up. And when they make their new bonds, you see we've got the dark dot and the light dot. When they make their new products, they've released such a little bit of energy that the net and overall energy is an intake of energy. Okay, lots of energy needed to break the bonds, which are strong. Okay, bond breaking is endothermic. Little energy is released when the bonds are formed, so therefore it's weak bonds, and those are exothermic. But now you can see that the heat needed was bigger than the heat released. The energy needed was bigger than the energy that was given off by the new products. Okay, and there you can see we have strong bonds of our reactants because they needed so much energy to break, whereas our products gave off such a little bit of energy that they probably did make a weak bond. Okay, because remember, the same amount of energy would be needed to break that. So more heat is added than released, and so that is endothermic. I want you to think of endothermic as inside absorbing it inside. Endo is within. Okay, so the heat is being absorbed. Okay, so more heat absorbed than what was released. Now, this might confuse you a little bit. My change in energy is greater than 0. Don't worry about that now. I will talk about that a little later in our lesson in the week. Okay, so don't worry about that. It's called looking at the enthalpy, or the heat of the reaction means that it's a positive. Basically what it means is that if you look at it overall, our whole reaction took in more heat than what it released, and so overall it has a lot of energy in it. Okay, so endothermic reactions absorb heat, thus decrease the temperature of the reaction mixture. So what happens is that if you had to put 2 liquids in and you held a beaker that was going there was an endothermic reaction in it, you would actually feel cold because it's trying to take in all the heat from the surroundings. But remember, things like baking a cake is endothermic. It requires the heat to make the reaction happen. So all these bonds need to break inside the mixture of a cake so that it can make new bonds. Okay, so anything that requires a lot of heat to react would be endothermic. Anything that you feel is cold. So sometimes those packs like Mrs. Felix has, where she breaks the thing and it goes cold, that would be an endothermic reaction because it's taking the heat away from you and trying to absorb that heat. Okay, so that is endothermic. So exothermic is obviously the other way around. The reactants require very little amount of energy to break apart. But when they make their new products, it releases a lot of energy. Okay, and so what can we tell from that? We can tell that our reactants had a weak bond and our products had quite strong bonds. Okay, so little energy needed to break bonds which are weak, lots of energy released when bonds are formed or strong. So heat needed to break the bonds is less than the heat released. So it was all this heat that is released, more than what was gained. Okay, so more heat released than needed, and so it is exothermic. Think of exo as exit, exhale, you're releasing it, it's coming out. All right, so more heat is coming out, so the net change in heat is negative. You lost more energy than what you gained. Okay, and that is often when you feel a beaker that's warm. I've let you feel some exothermic reactions before. Okay, so let's look at some real life examples. So combustion, that is the burning of anything. So if you light a match, that's combustion, and so that would be exothermic because it's releasing heat. Thermic. So even if you think of so anything that's making light and energy, that would be considered as exothermic. It's giving it off almost like a product. So if you're burning a candle, the product of that candle is you're going to get carbon dioxide and whatever other gases, but you want heat and you want light out of it, and that is energy being given off. Okay, photosynthesis, that's using heat, so that would be endo, or using the radiant energy. And cellular respiration we know is opposite of photosynthesis, and so it is exothermic. They are chemical reactions in your body that releases heat for your body to use. Okay, so I'd like you to please do Think Tank 13.1, number 2 and number 4. I hope you've been managed to download these notes, and yeah, I will be around if you need to ask me any questions. Okay, have a good day.